Hello students, in this video, I will be talking about the topic of leftist tree and also to check if a given tree is a leftist tree or not. Okay, so this is regarding the leftist tree with respect to the subject data structures and applications, and the subject code is BCS304. Okay, I have already made a video on leftist tree, but some students were having some confusion regarding identifying a leftist tree. So in this particular video, I'll be taking up some examples and I'll show you step by step how to check if a given tree is a leftist tree or not. Okay, so before I go to the checking part, first let us understand what is meant by a leftist tree. See, this part is usually asked in the exam. So remember this definition. Okay, a leftist tree is a binary tree such that if it is not empty, then shortest of left child is greater than or equal to shortest of right child. Okay, so condition is shortest of left child of a given node should be greater than or equal to the shortest of the right child of x of a given node. In this case, the node I have given it as x. Now you might wonder what is this left child, right child, what is this shortest and all. So when I take up an example, I will tell you what this is, what this condition means, and what is shortest of left child, shortest of right child, and so on. See, it is a tree, right? So it will have a root node and it'll have child nodes also like this. Correct. So how to do the declaration? So I have taken struct node as I will be using a structure for this struct node. So what are the parameters? See, first is a data part. So data part is with respect to this root node, data part. And left child, we are not sure if it is a leaf node or not. It might be, left child might become another tree altogether. So I'm just giving a pointer to the left child. Similarly, the pointer to the right child. Okay, a pointer to the left child and pointer to the right child. Then you have a special variable here called as rank. So I have given the explanation. See here. Here rank represents the shortest path from a node to a null pointer, that is a leaf in the subtree. See here, rank represents the shortest path from a node to the null pointer in a subtree. What does this mean? See, I'll take up this example. Here you see. Okay. See, uh, for this given node, let me talk about this node 2. See, node 2 is a leaf node here, right? So what we will do is, if you look at this tree is not a complete binary tree. It's just a binary tree. What do you mean by complete binary tree? Complete binary tree means every node should have exactly two child nodes. But if you look at the node 2, okay, node 2 is there, but does it have any child nodes? It does not have any child node. That is why it is not a complete binary tree. So I'll draw one, these nodes. I'll draw these nodes to make it as a complete binary tree. Okay, so I'll add these nodes like this. Okay, now 2 is having two child nodes. See, this is one child node, this is one child node. Similarly, 3 is also having one child node each on the either sides. Now, what does this rank mean here? Rank means from the given node, if I'm taking this node into consideration, that is node 2, from that node to the leaf node, what is the you remember like this, okay? From the given node to the leaf node, the number of paths, how many paths are present, that you keep it in mind. See, here if I take, I'll use another color here. See, from 2, okay, from 2 to, it has two nodes, right? Leaf nodes. So here, so from this leaf node to reach 2, how many paths did we cross? We crossed only one path, correct? Similarly, from this node to 2, to reach from this leaf node to this 2, how many nodes did I cross? 1. Correct? Here also I had crossed one node. Here also I crossed one node, as in like one path. So the you have to take the shortest. See, in this case, both are having one and one, right? So I will take any one of them. So suppose I had two here, okay? Here there were two leaf nodes like this. No, not two leaf nodes, no. Two nodes were like this. So from this particular node, in order to reach 2, I had to cross through two paths, right? So that time the left child would have become 2, right? And the right child is 1. So you have to take the smallest one. So I'm taking with respect to the right child. So that becomes a rank. So for a given node, if it is having left child and the right child, pick the child, okay, through which if I travel, I can reach the leaf node in lesser number of steps. Okay, that is how the rank is given. I hope it is clear. Now I will take up an example. See, this is the most popular question. This was there in the DS model question paper, okay, for 2023-2024. Since 2023-24, we have this scheme, 22 scheme. So this is a model question paper you have. So they have given a question saying, define the leftist tree, give its declaration in C. So define the leftist tree, it's over here. And its declaration is also there. So you can go through this. So definition is also there, declaration is also there. Next is check whether the given binary tree is a leftist tree or not. Explain your answer. Okay, so two trees are there. We'll look at each tree separately and we'll check whether the tree is a leftist tree or not. See, I have taken that tree here. Okay, first thing when you get a tree like this is check whether it is a complete binary tree. That will help you in doing the calculations. So here, if you look at the tree, it's a binary tree, but it is not a complete binary tree. Why? Because see, some nodes, for example, 25, if I take 25 can be a root, but it has no child nodes, right? So it is not a complete binary tree. So what you do is first thing you convert a given binary tree into a complete binary tree. Okay, take a binary tree and convert it into complete binary tree. So what I will do is I will add the left child and right child to each of this incomplete sort of nodes. Okay, so why have I written it in square? Because I need to know that these were not originally part of the tree. Correct? These are the nodes that I have added so that the tree becomes a complete binary tree. So this type of nodes which are already present, in this case 4, 8 and all that were present, right? So they are called as internal nodes, and these extra nodes which are in square, sort of like a rectangle only. You can, when we draw, you don't really care. It should be a square ideally, okay? So these nodes are called as external nodes. So here also see, 9 is not having any child nodes, so I will draw like this. Similarly, 13 is also not having the child nodes, so I will draw here. 40 is also not having, so I will draw for 40. Similarly, for 90. For all the other nodes, two child nodes are present. So now this has become a complete binary tree. Are you clear with this? First thing is make sure that your tree is converted into a complete binary tree. Okay. This is not mandatory, but this makes the simplification easier. Okay. Now what we will do is for each node, we will find the rank. If you remember, there was something called as rank here, right? Rank. So we need to find the rank. And based on that only, we can tell if a tree is a leftist tree or not. See, for example, I will start with from the bottom. So first I will take this 40 into consideration. 40 into consideration. But before 40 also, we have these two extra nodes that I have drawn, right? These external nodes. So the rank, if you remember, is what is a rank? It is in order to reach from the root, in order to reach from the leaf node in order to reach from the leaf node to a given node, okay, the given node, the number of paths we have. This is my understanding, okay, because this way it is easier to understand number of paths. Okay, see here. This itself is a leaf node. So from this node, in order to leaf node, how many paths do I need to cross? You don't need to, because this itself is a leaf node, right? So from leaf node to leaf node, what can you cross? Nothing can be crossed. So for this also, it would be 0. For all the leaf nodes, rank is 0, correct? For all the leaf nodes, the rank is 0. Okay. Next, check for the, you go to the other nodes and check. See, for the 40, I will consider, I will check for 40. Okay, see here. In order to reach from 40, sorry, in order to reach from 40 to the leaf node, how many nodes did we cross? See, this is a leaf node and this is a node I want to reach. In between that, how many paths did I cross? I crossed only one. Remember, it is only one. Don't write it. Okay, just keep it in mind. For the left child, it was one. And even for the right child, see, this is the right child and I have to reach 40. So I only have to cross one path, right? So here also it is 1. The rank is 1. Okay, so remember, uh, both for the left child as well as right child. Okay, if I need to go, I need to go through one path and one path. Now, what you have to do is, in order to give the rank for 40, you have to check out of the left child rank that you're getting and the right child rank you're getting, which one is the highest. So here I'm getting both are equal value, so I can assign any one. So 40 will get the rank of 1. Okay, I hope it is clear now. Now let us do for the right side. I'll do for 90. See, now I think it has become clear. So from 90 to the leaf node, from 90 to the leaf node, how many paths did I cross? I crossed only one path. Similarly, the right child also needed only one path, right? So, sorry, I think I accidentally deleted the lines. Wait. Wait, let me okay, so this is how it is. So now I will write the rank of this one. I hope it is clear. Now let us do for 25. 25 also, it is having only one, see, one path, right? To reach from the leaf node to itself. So it's right now it is 1. Here also for the right child also it is 1. So both are equal. So I can assign any one value. So I will take that rank as 1. Okay. Similarly, I'll do for 20. Let us do for 20. Okay. So 20, see, 20 is here. In order to reach from the given node 20 to the leaf node. So one possibility is going here, then taking this path. So I'm getting 2. The other one is from here. I'll use another color. From here, then here. So 2, right? So it is 2. Similarly, here to here, 2. Here to this path is 2. See, all are 2 only. So there is no confusion. So what you can do is, you can choose any one value. So I'll choose it as 2 itself. All are equal only. So it will not make any difference. So 2. Similarly for 9, 9 also, if I want to reach this side, it is 1, and this side left child also 1, right also 1. So I will consider it as 1. Similarly for 13 also, it is 1. Correct? Next, for 5. So for 5, if I want to go one way is this, the other way is this one, the third way is this, and the fourth way is this. All will have two paths in between them. So again, this is going to be 2. Okay, 1 minute. Here we had a node, that's why. Okay, so this is also going to be 2. Now, let us go to the main node 4. So many possibilities are there. Okay, so check for this one. Once you get a hold of it, it will become easier. Okay, so you need not check every single node. See here, in order to reach 4, I have to cross this one, then I have to go here, and then I have to go here. 3. In other ways also, it is 3 only. You can check. So here to here and this way, third. So there also it will be 3. So everywhere it is 3. So for the left child, for 4, I'm keeping it as 3. Let us look at the right child. See, for the right child, if you see here, I'll use the color orange. See, one way to reach 4 is from here, then here, and then here. Right? The other way, there it is 3. Okay. Remember? And if I go from this way, it is 1, 2, 3, and 4. So 4. So if you remember, I have to choose the smallest one. So I'll eliminate this. So from the right side also, I'm getting 3. Okay. So I'll choose 3 here. Okay. For 8, it is 2. Okay. Now check. Now you have done all this, right? You have written the ranks for each and every node. Now you will have to check whether this condition holds true for every node in the tree. Shortest of right child of x. Here also shortest of. See, for example, let me take the node. Let me take the node 40. Let me take the node 40. Check if it is, if the length of the this left child, okay, that is 0. Is it greater than or equal to the length of the right child? Not length, the shortest of the right child. No, they're equal, right? So it is, this one is a valid node. Similarly, check for this one. See, 90 is a node. Its left child is having the rank 0, that is shortest. Here also there is 0. Okay. So what is it satisfy this condition? Left child is 0. Right child is also 0. So it is greater than or equal to 0, right? So this is also satisfying. Similarly for 25, 0 and 0. So this also will satisfy. Here for 20, it is 1 and 1. So this also is satisfying. When it comes to 8, okay, see what 8, when it comes to 8, left child is 2, right child is having 1. So left child is greater than or equal to right child because left child is 2, right child is 1. Okay. Similarly, in the other side also it will be holding true. When it comes to node 4, its left child is having the value 2, which is greater than or equal to its right child, right? So all the nodes are satisfying this condition. So you can say that this particular tree is a leftist tree. This particular tree is a leftist tree. I hope it is clear. Now they have also told explain your answer. So how will you explain the answer? You will have to tell that this particular tree given is a leftist tree because every node satisfies the condition of a leftist tree. That is, every node is having shortest of left child of x greater than or equal to the shortest of right child of the x. If you want, you can take up one node also. You can say that, for example, for the node 4, its left child, shortest of the left child is 2. Okay. And its right side, the shortest of the right child is also 2. So 2 and 2, which is satisfying the given condition. That is why the given tree is a leftist. Okay, I hope it is clear. Let us go to the next example. Here is where the confusion was there. So let me explain. First thing, I hope you know you have to add the left and the right cell to make it as a complete binary tree. So here also for 10 also I will add. Then if you look at 5, 5 is having a left child, but it does not have a right child, right? So here also you add one. Now this has become a complete binary tree. Okay, now check for that rank. See, in order to reach from the leaf node, I will have to only cross one. I don't have to cross anything. So 0, here also 0, here also 0, 0, 0. Okay, and here also it is 0. All the leaf nodes will have 0. When it comes to the child nodes, see 6. Okay, if I take 6, its left child is having, in order to reach from the given left child to its node, we only have to cross one path. So we have 1 as the left side. Right side also it is 1. So I'm taking the shortest among the two. There is nothing to be like, don't have to worry, because both are 1 only. So I'm taking 1 here. So 7 also it will be 1. For 10 also it will be 1. 9 also 1, and 8 also 1. Okay. Now when it comes to 3, let me take 3. 3, okay, is a node. 3. So in order to reach its left child, from the left child, if I want to reach the root, I have to cross the 2 paths. Okay. So for the left side it is 2. For the right side also I need to have 2. Right. Similarly, from here to here also I will have 2. So everything is 2 itself. So, okay. So this will be having the value as 2. Okay. Similarly, for 4, 4 also, if you see, you'll be getting the value as 2. Whereas for 5, can you tell me what will be the rank of 5? See, for the 5, if I'm taking through the left child, so I will have to cross 2 paths. Okay. So like this, 1 and 2. But if I take the right child, I only need 1. So you will have to choose the shortest among the two. So one side I need 2 roots. The other side I only need 2 edges. So, oh sorry, 1 edge. So I will choose the shortest of them. So I'll choose 1. Okay. Similarly for 2. So if I do all the other nodes, okay, if I consider all the other nodes, I need 3 paths. 3 paths. Okay. So for example here, so 1, 2, and 3. This is also 3. See, 1, 2, and 3. Here also it will be 3. All the other paths will be 3. But if you look at this special case here, this path. So 1 and 2. Can you see here? 1 and 2. So it's just 2. So what I will do is I will write 2. The left child is having 3, right child is having 2. So I've taken the shortest among them. Then when you look at your main node, that is 1, again you will have to check. So from here 1, 2, and 3. Okay. So from here 1, 2, 3, and 4. Is there any shortest path other than that? Check. So 1, 2, and 3. That is the shortest path. So here also from the left child I'm getting 3. Right child also I'm getting 3 itself. Okay. So for the left child also I'm getting 3. Right child also I'm getting 3. So I will choose that itself. Okay. So here 3. Now check that condition. Left child is greater than or equal to right child. So For 6, left child is greater than or equal to right child, it is satisfied because 0 and 0. So 0 is greater than or equal to 0. Similarly, for 7, it is greater than or equal to 0. For 1, it is greater than or equal to 0. It satisfies. Okay. What about 5? So for 5, left child is 1 and right child is 0. So left child is greater than or equal to 0. Similarly, for node 1, left child is 2, having the value 2. Right child is also having the value 2. So it is great. Shortest of the left child and shortest of the right child is greater than or equal to the right child. So this is also a leftist tree. Many were having confusion with this one, but in this case, this is also a leftist tree because that condition is satisfied. Now I'll take up one more example, and this time I will give a different type so that you can understand. See here, I have a node called A, then B, C, D, E, and F. This is a tree I have. Now let us check whether this tree is a leftist tree or not. First thing, make it as a complete binary tree. So add the external nodes. C is only having right child, so add one left child. Now find the rank. So for this one it is 0, here also 0, all the child nodes 0. Okay. Then consider for F. For F, if I need to reach from the leaf node to F, I need to only cross one node, one path from either of the sides. So I'm taking this value as 1. Similarly, for D, it is 1. E, it is 1. Okay. And what about B? B, if I want to reach, then I'll have to go from here, then here. Correct? Similarly, if I take from the right side, it is also having the same value. So it is 2 and 2. So here, the value becomes 2. Okay. Now let us look at C. For C, okay, from the right child, if I go, then I will have to go from here 1 and 2. From the right child, I'm getting the value 2. But from the left child, I only have 1. Okay. So I'm taking 1 here. This is a rank. Okay. So C will have the value 1 here. Similarly, A, if you look very carefully, 1 and 2. So that will be the shortest. I hope you have understood. So I'll not check for the other nodes. So I'll consider this to be 2. Now you check if this condition holds or not. Shortest of left child of X, is it greater than or equal to shortest of right child of X? So for D, it is okay, 0 and 0. So this is okay. For E, again 0 and 0. So E also okay. F, 0 and 0. Okay. But look at the node C. Look at the node C. C's left child is 0. Right child is having 1. So left child is having 0. Right child is having the value 1 shortest. Now see here. The condition is not satisfying. 0 is greater than or equal to 2. Greater than or equal to 1. Is it? No, it is not. So I can say that here in this part, the condition fails. This condition fails, right? So you can say that this is not a leftist tree. This is not a leftist tree. Why is it not? Because at node C, if you take node C into consideration, shortest of its left child is 0, whereas shortest of its right child is 1. It is 1. So 0 greater than or equal to 1 is untrue. That is why it is not a leftist tree. I hope you have understood and this confusion now has got cleared. So you have to first, the step for checking if a tree is a leftist tree or not, first you do is, what you do is you convert the given tree into a complete binary tree. Then for each node, you find out the rank. Okay, each node, including the external nodes. External nodes, anyways, it will have the rank as 0. Then you check if this condition is satisfying or not. What? That is shortest of left child greater than or equal to shortest of right child. Every node should satisfy that condition. Okay, if any of the node, see if there are 10 nodes and if 9 nodes are satisfying and one node is not satisfying, still it is not a leftist tree. I hope it is clear now. So you can go through this. Okay. So 3 examples I've taken, 2 with leftist tree, 1 not being a leftist tree. So I hope the doubt is cleared. Okay. And in the next video, I will be coming up with some more interesting topics. Till then, thank you so much.